Alright, now before we move on to the next topic, we're going to look at one more example involving the Mann-Whitney test. This is going to be example 3.3, and this is going to be a one-tailed test. The first two examples that we looked at in this section were two-tailed tests, but I wanted to show you an example of a test that involves a one-tailed test. Alright, so let's look at this. So, an experiment was conducted to evaluate the effectiveness of a new diet for steers. 18 steers were available for the experiment. 8 were randomly assigned to the regular formulation, and the remaining 10 were assigned to the new formulation. The weights of the steers at 1 year are given in the table below. So this is a little bit different situation than the other two examples in that, in this case, we don't frame the question or phrase the question in terms of sampling from two populations. We have a group of steers, 18 steers, that we can use for the experiment, and instead of randomly selecting from a population, we are randomly assigning steers to the new diet or the regular diet. It's going to result in the same kind of analysis, but there is just a little bit of a difference in the way that we think about it and the way that we phrase it. Regardless of whether you're sampling from a population or doing a designed experiment where you are assigning your experimental units, in this case the steers, to a treatment, it's important that you do it randomly. Randomization, whether you're randomly assigning treatments to your experimental units or randomly selecting experimental units from populations, it's that randomization that creates the probabilistic structure, that probabilistic framework that gives the validity to the analysis. And in fact, it's the randomization that, in this case, leads to the sampling distribution of the test statistic under the condition of the null hypothesis, which we've been looking at in the previous lectures. So if we didn't have randomization, then those distributions would not be appropriate. We wouldn't know what the distributions are. So the purpose of randomization is to create that probabilistic framework within which we can do valid analysis. So the question here, we've got the regular diet and we've got the new diet, the new formulation. And so the question is there sufficient evidence at the 0.025 level of significance to conclude that the new diet results in higher weights? So there are a couple things here. Number one, we're using a little bit of a different significance level, 0.025. And the reason we're using that is because we're somewhat limited in the significance levels that we can use when we're doing the exact Mann-Whitney test using the tables that we have access to. Remember that in that set of tables, we only have a 5% significance level table and a 1%. And the other thing to keep in mind is that those significance levels for those tables are two-tail significance levels. So we'll see as we go along here that we're not able to do a 5% level test using that table, but we can do a 0.025 level test. So we've got the data here, and in fact this setup, the number of observations in sample A, the regular diet, and the number of observations that we had in sample B, the new diet, those are the same sample sizes that we had in example 3.1. So this has the same structure from that standpoint as we've got here. So anyway, but we can see the values here. Let's take a look at the hypotheses to be tested. So in this case, the null hypothesis is that the two diets are the same. The alternative here is not just that there's a difference, but there's a specific kind of difference, and in particular, that the new diet results in higher weights. So if we were going to express that or describe that in terms of a population of values, which is ultimately what we're talking about here, then we would say that the new diet results in a population of weights that is shifted to the right of the population of weights that result from using the regular diet. So this is not a two-tailed test, this is a one-tailed test. Now, is it a right-tailed test or a left-tailed test? Well, the way that we expressed it just now, it sounds like a right-tailed test. But remember, we've got two sets of labeling. Here, let me go back to the previous slide. We've got labeling that we use to describe the experiment. And so we've got a regular diet and a new diet. A is a regular diet, B is a new diet. But we also have to have a set of labeling that corresponds to the analysis. And remember, all of this is driven because of the structure of the table. And so we really have to first assign our what we're calling 1 and 2 labeling, which is utilized for the analysis. That labeling, that 1 and 2 labeling, is based on the relative sample sizes. And again, there are 8 observations for diet A and 10 observations for diet B. And so we're going to use the label 1 to correspond to diet A, the regular diet. And we'll use the label 2 to correspond to the new diet, which we're also calling diet B. Sample 1 corresponds to the sample of year 1 weights of steers under the regular diet, diet A. Sample 2 corresponds to the sample of year 1 weights of steers under the new diet, diet B. All right, so once we assign that labeling there, then we can label the populations as well. And so population 1 is the population of year 1 weights of steers under the regular diet. Population 2 is the population of year 1 weights of steers under the new diet. With that labeling, then we can state the hypotheses in terms of populations 1 and 2 in the following way. The null hypothesis would be that population 1 and population 2 are the same. The alternative hypothesis would be that population 1 is shifted to the left of population 2. You could also say population 2 is shifted to the right of population 1, but I like to express it this way to keep things consistent with how we've set things up generally in the notes. With that set of hypotheses, then we're going to use a rejection criterion with a significance level of alpha, and so the rejection criterion is to reject the null hypothesis if our test statistic is less than or equal to the appropriate critical point from the appropriate table in the set of tables that are called A10. Now again, this subscripting here with the 2 alpha could be a little bit confusing, so let's clear that up. So we want to get the 2 times 0.025 or 0.05 critical point from the table. So that means we have to use the 0.05 table. So this explains what I'm talking about right down here. All right, so think on that and let me know if you've got any questions. Okay, so again, our sample sizes, 8 and 10. We're talking about our rejection criteria here. So we need these sample sizes to look up the appropriate value in the table. This is a one-tailed test with a significance level of 0.025. And so from table A10, the way the table is set up, every test is a left-tailed test. That's the way it's formulated. So we're going to reject the null hypothesis if our test statistic is small, less than or equal to some value. So the question is, what is that value? By the way, because of the nature of this test, the test statistic is T1. Okay, so points to remember. The table, as we've been talking about, is designed for 2-tailed tests. Since the desired significance level is 0.025, we will need to use the 0.05 table, 2 times the 0.025. All the tests are left-tailed tests when using table A10, and the inequalities are non-strict. Remember that, okay? We use less than or equal to rather than strictly less than in specifying the rejection criteria. All right, so N1 is 8, N2 is 10, and we're going to use the 0.05 level table. And so let's just take a look at that. And so we see that our critical point here is going to be 53. And so I can come back here. Our rejection criterion is to reject the null hypothesis of our test statistic T, which is T1, if that is less than or equal to 53. T1 is equal to 46. And then for completeness sake, I'll calculate the conjugate of T1, so T1 prime, and that turns out to be 106. And because this is a one-sided test, and in particular, it's version 1 of the 2 one-sided tests that we described and looked at, the test statistic is just equal to T1. So the test statistic value is 46. Now, how did we get that? Well, again, I've got this spreadsheet that I created for this purpose. And so I've got my data in the spreadsheet. So this column contains my diets, 8 observations under diet A and 10 observations under diet B, along with the weights. And then what I need to do is I need to sort, create an ascending data array based on the weights. And then in addition to that, what I need to do is I need to, let me see here if I can zoom in. There we go. All right, so I need to, after I create the ascending data array based on the weights, then I have to assign ranks. And there are no repeated values here, so the ranks are just the integers from 1 up to 18. And then again, I've got these 2 columns programmed with formulas so that for this column, it's going to pluck out those ranks for experimental units that are under diet A. And then in this column, right, it's going to pluck out the ranks for which the diet is B. And then down here, I calculate the sums of those columns. All right, so this is the rank sum for the sample under treatment A, the rank sum for the sample under treatment B, and then doing these calculations according to the formulas in the notes and all that. T1 is 46. The conjugate of T1, so T1 prime is 106. And so that's where I got those values. And okay, let's see here. Let's get back to regular size. All right, so T1 is 46, T1 prime is 106, and then again, the test statistic is 46. And so again, the rejection criterion was to reject the null hypothesis if our test statistic is less than or equal to 53. The test statistic is 46, that is less than or equal to 53, and so we reject the null hypothesis. Our rejection criterion has been satisfied, and so we reject the null hypothesis. And so we can say that there is sufficient evidence at the 0.025 level of significance to conclude that the new diet results in higher steer weights. The next thing I want to do, I want to continue with this example, but I want to use, let's illustrate using the large sample approximation to the Mann-Whitney test for this one-sided test. So just to kind of review and to reiterate what we were saying in the last lecture, that the large sample approximation to the Mann-Whitney test uses the normal distribution with the same mean and standard deviation as T1 to approximate the true sampling distribution of T1 under the conditions of the null hypothesis. All right, so it's using this normal distribution as an approximation. And so how good is this approximation? What can we expect? Can we expect it to give us a good result, an accurate result? Well, what does the true sampling distribution of T1 look like under the null hypothesis? How well should we expect the normal distribution to approximate this true sampling distribution? All right, so I've constructed the true sampling distribution of T1 under the conditions of the null hypothesis. And so here it is. Now we saw that before in example 3.1. It's the exact same sampling distribution of T1 under the conditions of the null hypothesis. And that looks really, really normal. We can certainly envision superimposing a normal curve on top of that, that has the same mean and variance, and it would fit that very nicely. So we can expect to get pretty good results with this, even though the sample size, the total sample size, is only 18. So let's see here. So the sample sizes were 8 and 10, as we know. And we know that T1 was 46, and using this large sample approximation, the test statistic T is always equal to T1 in this large sample approximation. Okay, so we need to calculate the mean and the standard deviation of the sampling distribution, the true sampling distribution of T1. Okay, so the mean is equal to N1 times N1 plus N2 plus 1 all over 2. Okay, so the mean of the sampling distribution of T1 under the conditions of the null hypothesis is 76. And the standard deviation is given by this formula, and that works out to 11.2546, rounded to 4 decimal places. Let's recall how things were labeled here. We used the 1 label to represent steers under the regular diet, and the 2 label to represent steers under the new diet. And so because of that, here's what the hypotheses look like. So the null hypothesis is that population 1 and population 2 are the same, and the alternative is that population 1 is shifted to the left for population 2. All right, so this is going to be, in this context of the approximate test, it's going to be a left-tail test, and we are using a significance level of 0.025 to be consistent with what we did when we did the exact test. So the rejection criterion is to reject the null hypothesis if the standardized version of our test statistic z-calc is less than negative 1.96. And so now we calculate the value of the test statistic. So we have t, which remember is T1. Okay, so that was 46. We subtract off the mean of its sampling distribution, which was 76. We then divide that difference by the standard error of t under the conditions of the null hypothesis. So that is 11.2546. All right, and so we get a calculated value of the test statistic equal to negative 2.67. Now remember that the p-value is, now okay, I see here I've got a typo. Let me fix that real quick. Okay, abracadabra, that got fixed. Okay, so the p-value, because this is a left-tailed test, right, is equal to the probability that the standard normal random variable is less than or equal to negative 2.67. And that p-value then, that probability, is 0.00379. Okay, so then we can draw our conclusions. Since the test statistic, negative 2.67, is less than negative 1.96, or equivalently, since the p-value, which is 0.00378, is less than or equal to 0.025, the rejection criteria have been met, and therefore we reject the null hypothesis. There is sufficient evidence, and I see another typo here. So there is sufficient evidence at the 0.025 level of significance to conclude that the new diet results in higher steer weights. That's how we can apply the large sample approximation to the Mann-Whitney test. And again, we are not assuming that the great thing about this is that we get to utilize the standard normal table as part of this approximation to the Mann-Whitney test. But the Mann-Whitney test does not have built into it, in terms of its development or its derivation, it does not have built into it any assumption about normality at all. And so we can apply this in all sorts of different situations. It's going to be applicable to more situations than a t-test or a two-sample t-test would be, but we still get to use the standard normal table to look up critical points and calculate p-values for really moderately sized samples. I mean, the total sample size is only 18 here, and yet based on this graph that we saw, again, this is the distribution. This is the true sampling distribution of t here, and that's the distribution that we're wanting to approximate. And because that is so nicely bell-shaped, it's got that unimodal and it's symmetric, and we can see visually that a normal distribution would fit over the top of that very nicely. And so anyway, this is a really great technique to be able to use, to have the robustness and the nonparametric characteristics of the Mann-Whitney test, but to be able to approximate that test and not have to use the table if it's inconvenient for us. We can do this by using the large sample approximation. Okay, and so just to give us an idea of the quality of the approximation here, at least in terms of calculating the p-value. So this is the approximate p-value. The true p-value is 0.00311. And so we can see that there's good agreement there. They're pretty close. And so the approximation that we got from the standard normal table, 0.00379, nicely approximates the true p-value, 0.00311. Okay, so that is the end of this example. It's going to be the end of this particular video. And I hope that was helpful to you to see a one-sided test, a one-tailed test, in the context of the Mann-Whitney test, both using the exact test and also the large sample approximation to the Mann-Whitney test. Okay, so in the next video, we're going to get into a generalization of the Mann-Whitney test. The Mann-Whitney test is used, again, to compare two populations using independent samples. We're going to use a technique or a procedure that is a generalization, or can be thought of as a generalization of the Mann-Whitney test, and it's going to allow us to compare two or more populations using independent samples. So I will see you in the next video.